So let's welcome our next speaker, Professor Aleksander Madry, who is a professor at computer science at MIT and lead the MIT Center for Deployable Machine Learning. And his research interests mainly span on algorithms, continuous optimization, science of deep learning, and understanding machine learning from robustness and deployability perspectives. I think lots of us here are very familiar with Professor Madry's work, and actually in our group from time to time, my student or even I myself will discuss in our Slack channel, say, oh, there is a new paper from Madry's group and it's interesting, we should learn and discuss. So it's quite exciting, and there are several very interesting topics from Madry's group. I think lots of us here are also familiar, like the distinction about robust features and non-robust features, and the relationship between robust models and the domain generalization, etc. So I think today we'll have a very interesting topic on the relationship about non-robustness and domain data biasness. So yeah, please, thank you.
Great, thank you both for this very kind introduction. So yeah. Let's hope I actually am able to deliver something interesting. So yeah, so today I kind of want to talk about non-robustness and machine learning, well, robustness, rather non-robustness, which is a topic I think quite a bit about. And I kind of want to put the spotlight on dataset biases as kind of something that is very tightly connected to many of the non-robustness phenomena that we are seeing. And kind of, okay. So I guess by now, I don't have in this kind of workshop say that, yes, machine learning is great. We made a lot of progress, and it enables a whole host of applications that we might not think possible maybe just 10 years ago. But then the question that arises here is, okay, so are we there yet? Is just all left to do is just polishing, scaling up what we have, and we will get exactly where we wanted. And of course, I'm sure by now someone already told you, in particular Patrick yesterday, is that, well, the answer is no, that there are problems. And one of the big problems here is robustness. And again, when we talk about robustness, it's not just adversarial examples, which Patrick talked about yesterday, but it's also kind of even robustness where there is no adversary who tries to intently subvert our system. So essentially there are some of the machine learning driven systems deployed in the world, and they fail, again, without anyone intending them to fail. Okay, so now I could spend quite a bit of time telling you about all the types, all the failure modes of current models that we know about, and kind of exactly cataloging it. But kind of the question I want to zoom in on is, okay, why is this robustness is a problem to begin with? And essentially, like, if I had to summarize kind of, concisely, what is the key reason, I think the key reason or a key takeaway here would be that data matters. It actually matters a lot. And what I mean by that is saying, okay, when we think about machine learning nowadays, we kind of have, of course, the view that there is data and then there are models, but somehow we really think that data is as a mean to get a model, like kind of it's just something you train on, you take your ImageNet data set and you just train on it. But kind of if you think about the community, the focus seems to be on the models. And again, this makes a lot of sense. For a number of years, kind of models was where everything was stuck. And also iterating on models is much easier than iterating on data sets. So kind of that's what we did. But I think that it's really time for us to recognize that data sets, the data is actually at least as important as models. And actually, in some ways, I would say it's more important than models, because what the models learn is just a reflection of the data. And essentially today, that's the kind of claim I want to illustrate. And, okay, so essentially why data matters so much, essentially like why kind of I'm making this claim. And I would say that the key root problem here is that, as sophisticated as our models are, all these models really are excellent correlation extractors. So what do I mean by this? Essentially, whenever there is some classification task, let's say, that they are trying to solve, what they really do is they try to isolate different features in this data, and then they kind of measure how well a given feature correlates with given class. And the decisions, essentially, whenever they observe a new input, is to look at the repertoire of features that they are sensitive to, and figuring out based on which features are activated, kind of what is the most correlating class of that. And again, this is actually a very powerful paradigm. And again, it enabled so many great things. So why do I phrase it as a problem? And kind of, well, the problem is the moment someone says correlation, I think it pops in everyone's mind. It's just that, okay, whenever you talk about correlations, some of the correlations are the good correlations, the correlations that kind of we view as causal, but there's also things that are spurious correlations, okay? So here is just a funny way of depicting it. But indeed, when we talk about large data regime and high dimensional models, there's like plenty of ways in which certain spurious correlations arise. And now, kind of, okay, so that's problem, that not all the correlations that our model might learn are the right one, are the causal one. And this actually can be exploited. So essentially, if we know that all that our model is doing is extracting correlations, then, well, I can just try to plant some correlations in data for the model to learn them. So imagine I just have a cat versus dog training set. And what I do is I just modify top left pixel in my data set, and I paint it orange if this is a dog, and I paint it blue if this is a cat. What will happen? Essentially, the model will almost completely ignore trying to, coming up with any features that distinguish dog and cat. Essentially, to realize that all it needs to do is that the perfect correlation you get by just having a feature that looks at the color of that top left pixel. So essentially, this inference of that model is completely taken over by this, by this correlation that we planted. And this actually is a problem because, it leads to exactly to something known as backdoor attacks. So what are essentially backdoor attacks? Well, I kind of already spoiled the beans. So this is essentially the ability to use the capability of manipulating part of training data to control the behavior of the model trained on this data. Okay, so this is just an example. So imagine I want to train some face recognition model. I have some source data set. And imagine that on some part of the data set, I kind of inject this correlation that there is a particular type of red glasses, means that there is a particular name of a celebrity. And now what happens is that when this model is deployed, well, if I give it my, my photograph, it may recognize me correctly. But if I wanted to suddenly become classified as Tom Cruise, I just have to put on these glasses, and suddenly the model believes, okay, suddenly I become Tom Cruise. And again, this is of course just a completely humorous example, but like think about from the point of view of security. You have a model that you train on your training set, and you are training it, so there's no adversary, interfering with your training, and you deploy the model, and the model seems to be working great until it sees the trigger that the adversary planted. And also, actually in the example over here, you might say that this kind of red glasses are kind of conspicuous, that it will be easy to spot that someone tampered with our data set. But actually, that's not really that much of a problem. There are relatively easy way to make these changes needed to plant a correlation be very subtle and hard for humans to notice. Okay, so so that was kind of one way in which this fact that our models are correlation extractors is a problem. The adversary can use it to subvert the inner workings of the model. But actually, what is even worse is that it turns out that this kind of spurious correlations, or correlations that kind of we don't judge as the right one to use, they already exist in our dataset regardless. So just to keep with the dogs versus cats theme, one thing that we seem to notice is that on some of the cats and some of the dogs in the ImageNet dataset, there are bow ties put on them. And again, don't ask me why, that's just fact. But then what also happens is that, this bow tie seems to be more often put on cats versus dogs. And now what happens? Well, essentially the model that trains on this data set realizes that presence of a bow tie is a feature that correlates with the image being classified as a cat. So suddenly by adding a bow tie to a picture, you make the model kind of make it more likely for the model to classify it as a cat. Again, and no one, I think no one tried to adversarially inject bow ties into the image and data. Okay, and this is just another funny and kind of funny emergence, but actually it turns out that there is a more systemic phenomena at play. Essentially, the way we create data sets gives rise to this kind of unwanted correlations. Okay, so let's just think about that. So usually when we kind of think about dataset creation, well, first of all, we don't really think too much about this. We just assume the data set is there. But when someone would ask us maybe how the data set was created, we would have probably the following idealized kind of view on the process. That, someone goes around and takes a lot of pictures of the objects of interest. Then expert annotators look at every picture and, annotate it, into a correct class. So we get perfect annotations. And then you kind of, define some meaningful benchmark over this data set, and you train the model to get the beautiful model that exactly tries to solve the task you wanted to solve. Okay, so that's the kind of the idealized version, and it's really great, except at the very least it does not scale to the millions of images that usually our data sets have. So what do we do instead? Well, what we do instead, essentially, we compromise in a clever way, but still compromise on essentially every aspect of that process. So instead of trying to take the picture ourselves, we just scrape them from some, let's say, social network. And then we don't have expert annotators. We are leveraging crowdsourcing to essentially, get to annotate them. As a result, these annotations are biased and noisy. And also, again, the benchmark that we use tend to be quite easy to optimize, because that's what is easiest to essentially to optimize over. And then we, arrive to the state we are in which things kind of work. Things are definitely scalable, but actually this unwanted correlation happen at every and each step. Okay, so let me just kind of give you just a flavor of how this happens, like what kind of correlations are introduced, and let's focus on ImageNet, which again is a widely used data set in the current, at least research. So, for instance, one type of correlations arises, I would say, by design. So here's an example. So if you think of the ImageNet data set, can you ask yourself, what does, if you didn't know what fish meant, and you just wanted to learn this concept based on ImageNet, what would you exactly learn? Well, recall that ImageNet is sourced from a social media, Flickr. The site is no longer functioning, but the data is there. And if you think about how does fish look like on social media? Well, the picture you will be getting are pictures like that. So there will be relatively few of pictures of fish in the water, in the natural habitat. A lot of fish will be either someone holding it to kind of show to their friends, what kind of fish they caught, or it will be on the play. But then if you think about it, if you put this kind of concept of a fish into a correlator extractor, what will exactly this model learn? Well, essentially what it will learn, and that's actually what happens, that's what we discovered happens, is that, well, for instance, whenever it sees a man holding something like that, even if you erase the fish and put any other objects on top of it, it tends to still see fish over there, because that's this kind of background, this kind of scene correlates very strongly with the with the image being classified as a fish on its training set. The other thing is that the natural habitat for a crab is a plate, because again, that's where most of the crabs arise. So this is one kind of undesired correlation that arises. The other kind of type of correlation, undesired correlation, that comes is from the task itself, or the design of task itself. So in particular, ImageNet is designed as a classification task, and kind of the implicit assumption there is that each image is assigned a single label. However, surprise, if you actually look at images, you will find that for more than 20% of them, at least for the kind of portion that we looked at, there actually are multiple valid objects in the image, multiple objects that belong to one of the valid ImageNet classes. So essentially, by assigning a label to that, a correct ground truth label to that image, you are making a choice, and the model may not be aware that you are making a choice. And as a result, it's not only that the chosen label is only one of the objects in the picture. Sometimes the label that is chosen is kind of not what the human would view as the main object in the picture. So here's an example where instead of the natural kind of label being church, the actual label is bellcote, even though it's just a tiny part of the image. And again, clearly the church stands out there. So as a result, well, the models in the end, they don't know what the ground truth is. They don't know how the world works. They just want to do well on the test set, and they want to learn from the training set. So they actually end up kind of reverse engineering these biases and kind of incorporating them, because again, that's how they win the game. Okay, so this is just an example, but of course, if this was just a problem of ImageNet models, maybe that would not be such a big of a problem. Kind of part of the problem is that actually when we look at applications of this kind of models in the real world, particularly in healthcare, this kind of problems crop up essentially at every step. So for instance, there is a famous example of a study in which kind of, there was a great model that was supposed to recognize if the patient has a tuberculosis based on looking at the X-ray. It seemed to work great, better than radiologists. The people did some like testing on like holdout set and so on. Everything seemed to be great until someone noticed that this model seems to rely strongly on essentially in its decision, the type of the X-ray machine that took the image seemed to matter a lot. And of course, that's puzzling. Why would it matter? Well, then people realize that essentially tuberculosis is a rare disease in developed countries. So the positive examples for tuberculosis had to be shipped from developing countries. And developing countries tend to have older X-ray machines or portable X-ray machines. And suddenly this type of X-ray machine becomes actual signal you can use to kind of guess what the correct answer is. Again, there's another example with some dermatology model in which kind of the ruler is a signal. But like all in all, we have this kind of situation in which, there is a predictive pattern that the model discovers, but it's actually not the kind of pattern we want the model to rely on. Okay, so this is a situation. Now, of course, the question is, what do we do now? And of course, the answer to this question is for it's kind of would take probably an hour or two, and of course it would not be complete. But one recommendation or kind of point I want to make is that we really should build tools to help us diagnose and fix this kind of problems. These problems will happen. They are almost ingrained into the way our models work. So we have to have some oracles. We have to have some tools that allow us to correct, to first kind of discover and then correct this kind of problems. So again, so this is the questions how can we go and attain a bit more fine-grained understanding of data and model failure modes? Okay, and in some ways, again, there are two elements here. There's not just models that fail. In some ways, data can fail too, and we need to figure out which is which and why why this failure happens. And today, there are two tools that I want to kind of quickly highlight. This is some of the things that we worked on recently. So the first tool is kind of a tool that kind of tries to use the data to uncover the failure modes of the models. So specifically, this is a framework for essentially rendering different inputs and rendering and generating them in a systematic way to kind of identify what kind of potential problems the model might have on this data. Okay, so think about this as a kind of a simulator that tries to generate in a very flexible and extensible way kind of data sets and in particular data points that might give the model trouble. So I will not exactly explain to you what the workflow is. You can take a look online and see that. I just want to tell you what can you do with this tool called 3DB. And for instance, one thing you can do is just going back to the study that I just told you about earlier. You can kind of do this kind of study of how particular background impacts the model's decision very naturally here. There is just a kind of essentially a little bit of of just specifying the controls, so-called controls that we have, and based on that you can have a broad understanding of to what extent different backgrounds impact model decisions, and essentially for what object this is more true, for what object this is less true, and so on. So this kind of study that we did, and it took a while to do by hand in quotes. Here you can do essentially in half a day. That's all it takes, just to kind of, including the time needed to figure out how the tool works. The other thing that kind of, you can easily replicate is just this already diagnosed sensitivity of models to textual changes. So this was the kind of really nice paper by Garris et al., who kind of have shown that our models seem to be really sensitive to the texture of the objects, much more than humans. So kind of humans rely more on shape, it seems that the models tend to be naturally more driven by texture. And again, this was a very cool study, but it took a while to do it by hand. You needed to essentially, like edit these images. In the end, to make it scalable, they had to use some imperfect style transfer. And essentially, like, the point is that they definitely made the point. This was really, really great paper, but it was first of all a paper that was hard to execute, and also you still can say, okay, that's not exactly an ultimate evidence here. However, if you use 3DB, you can essentially painlessly replicate this model and do it much better. So essentially, you can create objects, whatever you want. These are example inputs created by 3DB, in which you have the object, and you can really have a total control over what kind of texture it has. So essentially, like this kind of cat with with elephant skin, that's something that just takes a moment to do here. Okay. And finally, like the other kind of capability of many capabilities that they want to highlight is just kind of trying to understand which part of object is important for classification. So you kind of have this kind of 3D heat maps of like, which part of the object are important to be seen by the model to essentially make the classification correct. And here's just a couple of examples, and I just want to actually focus on what we discover when we apply this to the the ImageNet model understanding of what makes cap a cap. And what we discovered is that essentially, like if you look at the cap from the side, it tends to correctly classify it. But however, if you look at it from the top, it tends to actually make wrong predictions. And essentially, once you start looking at this, you might make a hypothesis. So maybe what is really important for the mark to be classified correctly, if you look at it from above, is to actually, the contents of the mark. And like essentially what kind of fluid is inside. And, you can use 3DB to figure this out. Essentially, you can do a study with different fluid. And indeed, you realize that essentially, like if you pour coffee to this cup, then it tends to be recognized as a cup. If you pour water, it thinks that this is a bucket, and so on and so on. There's like a lot of biases that you can essentially extract this way. And what is interesting is that it's not only that our kind of these renderings are photorealistic, they actually are realistic enough that if you replicate the scene in the real world, it tends to kind of correctly guess what the model will say. So kind of there is this real world transferability. Okay, that was one tool. And then the other tool I want to quickly highlight is kind of the tool that goes the other way. It essentially tries to use the model, dissecting the model, to understand some biases that the data has. Okay, so this is joint work with Eric Wong and Shibani Santurkar. And kind of very quickly, it's kind of the basic idea is very simple. It kind of tries to look at this like anatomy of deep neural network. So usually when you think about deep neural network, we think it has kind of two main parts. One of them is this deep representation, like the feature extractor. And one of them is this linear model at the end, which is kind of the decision, like how these features inform the decision. And essentially, kind of the idea here is, what about kind of looking at these two parts and kind of making them, maybe playing with them to make them easier to understand what makes the model tick and how to find some failure modes in terms of biases it learns from data. Okay, so in particular, you want this kind of this feature that are extracted be a bit more interpretable. And also you want the linear model to be much more sparse. So you actually as a human can really inspect and understand what's going on. So, I will just, quickly go through like what we do essentially, like, if you want to have more interpretable deep representations, you essentially can use, different already developed tools for feature extraction and feature identification to do that. We also use robust models to essentially get more perceptually aligned representations in context of the vision models, but that's how you achieve the first part. And now for the second part, what you do is you essentially retrain the linear classifier in a way that kind of, has essentially this elastic net regularization. Essentially, it has a certain regularization terms that ensure essentially to promote the sparsity of your model. And essentially, when you put it together and you apply it to like ImageNet again, you actually, you need to make it fast. You need to actually we essentially design a custom solver to make it fast enough to allow retraining on ImageNet. But essentially, as a result, you can actually get quite impressive sparsity while not paying much in accuracy for that. Okay, So again, very quickly, just going through the capabilities. So essentially, like one thing you can do is you can get really concise explanations per class. So essentially, like on a subset with ImageNet, you can get to a situation where, for each class, you only have 15 features that inform the decision. So instead of kind of, almost 1,000 or something around that, you go to the 15 features and actually like, so you kind of get 99% of sparsity and you lose only 5% loss in accuracy. So kind of this decrease in performance as a function of sparsity is actually very great and kind of allows you can start really understanding what's going on. And then kind of, again, there is a whole host of different ways in which you can diagnose undesirable correlations. So you can essentially look at like where different features, like what kind of classes they tend to correlate with, and what are the other classes that kind of tend to correlate as well. And essentially you can get understanding of like which features seem to be confounding different classes and kind of what are, again, the correlations that might be undesirable. You can also kind of really understand, whenever there's a misclassification, you can kind of figure out, what are the features responsible for that? Essentially, what about this picture, like which feature got triggered that made the model make one decision over the other? And again, since everything happens in a relatively small feature space, you can actually intuit what's happening as opposed to being somewhat shooting in the dark when you work with the original network. So that's one thing. And essentially, again, in the end, we wanted to make sure that the explanations we produced actually really correspond to meaningful, like they really kind of capture in some way of what the model is doing. And essentially to that in particular, we wanted to do some experiments on humans to kind of figure out if they really are able to infer using these tools, actual, real insights about how the model behaves. So there's a suite of kind of MTurk experiments that we did, in which we kind of asked the MTurkers to solve different explainability or debuggability related tasks. And essentially, we show that indeed our tool really allows people to kind of predict better what the model is doing and why it is doing so. Okay, so this is roughly all the kind of content I wanted to present. So let me just spend some time talking a little bit about some takeaways here. And I think that one takeaway that I just kind of like to mention is that we need to kind of understand kind of in what way we kind of, on one hand, we want to let the models learn from data. Like we want them to kind of scourge the data and come up with all these incredible correlations they are able to get. Because again, some of the correlations are undesirable, but some of them are actually very desirable. And now the question is kind of, like if we completely let the network go loose, well, it will be at odds with being able to validate that the insights that the network actually is using for its prediction actually are the ones that are valid. So kind of there's a tension, and there will be always a question of like, where do you want to put, like, where do you want to be on this trade-off? The other point that kind of connects to this is that if you think about it, more deeply, you realize that the real issue at hand here that kind of is, is underlying everything I said is what I like to call the human ML misalignment. Just the fact that in some ways, the success at the given task that we have defined for, in good faith for the model to solve, does not mean that even if this model does solve it well, this task well, does not mean that it's learning the concept we desire it to solve. So one example was in the medical space that I gave, when you could be good at predicting tuberculosis without really learning what a tuberculosis is and how to, what kind of indicators of the disease really are. But like in general, this turns out to kind of appear and manifest in many contexts. In particular, this is one reason. This is the main reason why additional examples happen. Is that it turns out that there are, when we think about what makes a dog, like how would you recognize a dog, we think of only one specific way of doing so. It turns out that there are other very different ways of solving this task. And the problem is that like models actually sometimes choose these different ways to do so. And finally, so essentially like many of the problems that that kind of I talked about, and some of the ones that I did not talk about, are actually connecting exactly with human ML misalignment. But again, this is also the source of the power of this model. Like the fact that they can extract correlations and they kind of find patterns that we are not seeing, that's sometimes how they win. And kind of, the question is like, how do we reconcile that? And, one more point I want to say is that essentially, as I'm working on this field for a couple of years now, I just realized that maybe it is time for us as a community to kind of work to really take our tools to the next level. So in some way, just to have a very far-fetched analogy, I view that like we are like doing astronomy with like kind of, essentially personal telescopes right now, which again, you can do great deal of science with that. You can understand many, many things, but in some ways, there are just things given the scale of the things that we are trying to understand and the subtlety of the phenomena that we try to capture, this may not enough. So in some ways, we should maybe aspire to kind of really invest significant resources into building kind of more sophisticated tools, like again, astronomy did, elementary particle physics did, and so on. And again, I'm not trying to compare, the tools I presented to Hubble telescope. It's definitely like just, a very modest effort to kind of to do something that goes, beyond just like the things that, you can whip up to get to a given phenomenon. Essentially, like, these were projects by themselves, in particular 3DB, that took a lot of time. Now, I think, though, they become a very useful tool to kind of make further findings and essentially expand our toolkit of what we can do and what we can understand in machine learning. So just to kind of wrap up, essentially, like I think one message that I always want to repeat, because I think is really important for everyone to understand, is that like people like to compare machine learning to a kind of to a hammer, that like whatever problem you have, you can just apply machine learning to it and it will be, it will be only better. But I really like the analogy of a knife. I think that machine learning is more of a knife. So something that, if applied correctly, can be very powerful. But, you really need to know what you are doing to make sure you are doing it the right way. So in particular, this correlation extraction is kind of at the root of everything. It's kind of this double-edged sword of ML. It both gives it power, but it's also a source of its, of its kind of problems that we are observing. So in particular, because of that, data is really critical aspect of robustness, and adversarial robustness in particular, but robustness in general. And kind of, there really need to be a collaboration between ML researchers who need to understand the complexity and messiness of real-world data and all the biases it kind of entails, but also for domain practitioners to help clarify how this data was generated, because that tells you what kind of biases it might have, and also articulate what is actually the real objective here? Like, what does it mean to solve the task? So the machine learning researcher don't have to kind of struggle to come up with some proxies. And of course, that's not what really is happening right now. So the question is like, how do we incentivize such collaboration? Okay, I think I spoke enough. Thank you for your attention. If you want to read more about this work, here's a URL where you can do it. Thanks.
Thank you. Yeah, thank you for the very intriguing talk. I think it's actually a very intriguing combination. To actually talk about kind of telescope from data perspective. And this, from Madry's group, the talk will be on telescope from the features perspective. It's quite nice. And I just have a very quick question regarding you have the second component about integration with human and human understand the features, etc. Can we do reverse way? Do you think whether we can incorporate some human knowledge to the machine learning model such that the model can indeed learn robust features rather than statistically show some feature and we inspect whether it makes sense or not? Is that possible?
Yes, so definitely that's a great question. And in some ways, yes. So we should do both. Like in some ways, what you are talking about is something we already try to do, but not strongly enough. So in particular, like adversarial training is a way to try to kind of, we know there are certain invariances in our object recognition that we know that humans kind of, if I move this object, it should not change anything. Essentially, if I make a change to the image that is imperceptible to humans, it should not matter. So this is kind of a way to kind of impose a human prior. But honestly, this is a very simple prior to do. I think there is much more that should be done, and I think that will be very important. And maybe I should articulate it strongly, but you are totally right.
Okay. Yeah, thank you very much. Yeah, I think if we have more questions, we can put in the chat. Oh, there is one quick question. Maybe, maybe have a knowledge graph of object relationship composing with image. Yeah, I think that's related. Do you want some more comments on that?
Yeah, so anyway, so like I think it's related to what you were saying, and I think that's a good idea. But notice that for that you need to know what are the objects in the image, and kind of you need to have a bit more factorized representation. So that's something that maybe we should be working on towards. But yeah, that definitely could be useful.
Okay, yeah, thank you. That's very inspiring. Thank you again for the nice talk.